Greetings, all. We're finally to chapter 5. We've made it. And here we go. And Jodie Foster here and her pet cheetahs, I guess. Binomial probability distribution and related topics. Binomial probability, section 5.2. All right, some focus points. List the defining features of a binomial experiment. In the video, Big Al gave you a formula. You see the first part of that. That's the combination formula. P is the probability of a success times R, the number of successes, times Q to the n minus R. All right. Here's the long and the short of it. We're not going to use the formula. There's a calculator function that takes care of this for us. All right. So I'm not going to worry about the formula at all. And he also talks about in the video a table. Well, if we got a calculator, it's pretty anticlimactic to go and use a table when our calculator can take care of everything for us. So we're not using a formula. We're not going to be using a table. Throughout this video, all right, I'm going to have embedded a lot of Vimeo videos. Now, you won't be able to see the video from a video, but when you actually download the actual PowerPoint, which I suggest you do because I've got about at least 6 videos embedded inside the PowerPoint, which walk you through solving some of the problems. On a TV game show, each contestant has a try at the Wheel of Fortune. The Wheel of Fortune is a roulette wheel with 36 slots, one of which is gold. If the ball lands on the gold slot, the contestant wins 50 grand. None of the other slots pay. What's the probability that the game show will have to pay the fortune to 3 contestants out of 100? And the problem here that we face is that the first and second and third contestant is the first, the 48th, and the 98th. All right, this was kind of makes this problem a little bit challenging, but we'll see how our calculator can take care of this. In this problem, the contestant and the game show sponsors are concerned about only 2 outcomes of the Wheel of Fortune. The ball either lands in gold or the ball does not land in the gold slot. This problem is typical of an entire class of problems and is characterized by the feature there are exactly 2 possible outcomes for each trial of interest. These problems are called binomial experiments, named after a Swiss mathematician Jacob Bernoulli. All right, so the features of a binomial probability experiment is a fixed number of trials. The trials are independent. All right, the outcome of one has nothing to do with the outcome of another. Each trial has only 2 outcomes, S denoted by a success and F by a failure. Now, success doesn't always necessarily mean something good. If we're talking about probability of 3 out of 100 people getting cancer, well, I wouldn't consider getting cancer a success, so it's purely arbitrary. All right. For each individual trial, the probability of a success is the same. We denote the probability of a success by lowercase p, and that of a failure by q. Well, we know that p plus q is equal to 1. All right. The probability of something happening plus the probability of the complement has to equal 1. Something's going to happen. So if you know what P is and you want to find Q, it's the 1 minus P, the complement rule. Q is equal to 1 minus P. But here's the deal. In using the formula, you would have to calculate Q. When we do this with the calculator is not concerned with Q. It just wants to know P. The central problem of a binomial experiment is to find the probability of R successes out of N trials. Let's see how the Wheel of Fortune problem meets the criteria. We'll take the criteria one at a time. Each of the 100 contestants has a trial at the wheel, so there are trials. Okay. Assuming the wheel is fair, trials are independent since the result of one spin of the wheel has no effect on the results of the other spins. We're interested in only 2 outcomes of each spin of the wheel. The ball either lands on gold or it does not. Let's call landing on gold a success, especially for the contestant, and not landing on gold a failure. In general, the assignment of terms success and failure does not imply good or bad. I just mentioned that above. Talking about someone contracting cancer, you wouldn't call that a success. Or even contracting COVID-19. On each trial, the probability P of a success landing in gold is 1 chance out of 36. Favorable is only one slot that's gold out of a total of 36 slots, 1 chance in 36. Consequently, the probability of a failure, Q, is 1 minus P, or 1 minus 136, and that's 3536. Here again, if you were bound and determined to use your formula, which I don't see why you would, you have to, given P, you could calculate Q by taking 1 and subtracting whatever P was. We want to know the probability of 3 successes out of 100 trials. So in this example, it turns out that the probability the quiz show will have to pay the fortune, the 50 grand, to 3 contestants out of 100 is about 0.23. On my last slide, I'll show you how that answer, well, I'll let you do the problem. I'm going to show you how the answer comes out to be 0.23. The central problem of a binomial experiment is finding the probability of R successes out of n trials. Now we'll see how to find these probabilities. Suppose you're taking a timed final exam. You have only three. You have 3 multiple choice questions left to do. Each question has 4 suggested answers, and only one of those answers is correct. You only have 5 seconds to do these 3 questions. You decide to mark the answers on your answer sheet without even reading the questions. Assuming that your answers are randomly selected, what is the probability that you get 0, 1, 2, or all 3 of those questions correct? This is a binomial experiment. Each question can be thought of as a trial, so there are 3 trials, 3 questions. The possible outcomes on each trial is a success, indicating you get the correct answer, or a failure, meaning your answer was wrong. The trials are independent. The outcome of any one trial does not affect the outcome. Whatever you answer on one question has nothing to do with how you answer the other question, multiple choice. What is the probability of a success on any one question? Since you are guessing and there are 4 answers which to select, the probability is 1 chance out of 4. There's only 1 out of the 4 that's right. 1/4 as a decimal 0.25. The probability Q of a wrong answer is 1 minus 0.25 or 0.75. In short, we have a binomial experiment. You have 3 trials, 3 questions. Probability of a success P, 0.25. Probability of a failure, 0.75. Now, what are the possible outcomes in terms of successes or failures for these 3 trials? Let's use SSF to mean success on the first question, success on the second, and that F would be a failure on the third. Now, here's the situation here. All right. There are 8 possible combinations of S's and F's. You could get all 3 correct, success, success, and success. You could get all 3 wrong, failure, failure, failure. But notice, you get the first 2 right, the last one wrong, or the first one right, the second one wrong, and the third one's right, or I get the first one wrong and the next 2 are correct. You see what's going on here. All right, SFF and FSF, all different ways of arranging those 3 different items. All right, another way of thinking about it. The first question can either be a success or a failure. There's 2 outcomes. The second one could have 2 outcomes, and the third, 2 times 2 times 2 is 8. That's why my sample space here is 8 items. To compute the probability of each outcome, we can use the multiplication law because the trials are independent. For instance, the probability of a success on the first 2 questions and a failure on the last is P times P, a success and a failure, or P times P, better known as P squared times Q. Well, P squared, if the P is 0.25, 0.25 squared times 0.75, and doing the math, approximately equal to 0.017. Right? Now, the idea is there's 3 different ways that you can get 2 successes and a failure. All right. You have the first 2 questions right, third one wrong, or maybe you get the first and the third one right, or maybe you get the first one wrong and the second and the third one. So there's 3 different ways that can happen. And each of these, you've got 2 successes, which means you've got P times P or P squared times Q. All right, so kind of spelling it out, it gets a little whatever complicated, but you're seeing why. Since there's 3 different ways of getting 2 successes, you can see how we get involved in combinations. How many ways can I have 2 out of 3 right? Combination, or it doesn't make a difference. Now we can compute the probability of our successes out of 3 trials. for r equals 0, meaning you get none of them right, or 1 or 2 or 3. It says let's start by computing probability of getting one right. All right, one success. For 3 trials, there are 3 different outcomes that have exactly one success. All right, the first one right, the last 2 wrong. You see them, the first one wrong, second one right. Or maybe you get the first 2 right and the last, like first 2 wrong and the last one right. 3 different ways that can happen. All right, so each of these here, you've got one success. You've got one P and you got 2 failures, or Q. A Q times a Q is a Q squared. It happens here, it happens here. So you can see there's 3 different ways that can happen. And these 2 remain constant, the P and the Q squared. There's a P, there's 2 Qs. There's a P and the F, and F means those are Qs, failures. There's your P and there's your 2 Qs, all right? So 3 of them. So doing the math, no big deal here. 3 times 0.25 times 0.75 squared. But the 3 denotes, hey, how many ways? That's a combination. How many ways can I have one success out of 3 trials? He goes through this again, same thing. This little chart. Now, I actually do this problem out, and I don't know if this would record now if I play this. All right, I'm not certain that that's going to come out on this video. So moving forward, when I get to a screen that has a video of me using a TI, I'm just going to go right by it. But I suggest, not suggest, I strongly, it's a suggestion, is when you actually download the PowerPoint, actually watch each one of those separate videos because I walk you through how it's done on the calculator. All right, so there's this formula. There's no need to remember that. All right, we know P is a probability of a success. Q is 1 minus P. Your calculator doesn't need to know that. This is all information. Is if I didn't let you use a TI, which would be crazy. I mean, why? The calculator is meant to do the tedious tasks that we don't want to do. But it's important that you actually download the PowerPoint and actually watch those videos that are contained. And I'll talk about them as I get to each slide. Privacy is a concern for many Internet users. One survey showed that 59% of Internet users are somewhat concerned about the confidentiality of their email. Based upon this information, here's the key to the problem. What's the probability for a random sample of 10 Internet users? 6 are concerned about their privacy. All right, it's a binomial experiment, 10 trials. We assign success to an Internet user being concerned about privacy of their email. Therefore, P is 59% or 0.59. We are interested in the probability of 6 successes. So my R value, which is synonymous with X, because in the calculator doesn't have an R, but it uses X. R and X are one and the same. As far as, excuse me, doing it on your calculator. All right. So there's the information. We would not have to use this in our calculator. And once again, you're giving R, number of successes. In the TI, this is, instead of using R, they use X. X and R are one and the same. All right, there's like the formula. And, I wouldn't want to do this, and I certainly wouldn't want to go to a table, all right, to do all this. And we know the answer is 0.25, doing it with the formula. All right. If you watch this video out of the PowerPoint, I actually do it all out. All right. We can see. I calculate calls for 10 trials. N is 10, my P is 0.59, and my X value is the same as my R value is 6. Now, on the very first video contained in this homework assignment, I show you the difference between an 83 and an 84 calculator. Now, I say 83 and 84, you may have an 84 that has an older operating system, so it behaves like an 83. When you hit binomial probability density function, second function of ours, and you arrow down, on the 83 or an 84 that behaves like an 83, it doesn't prompt you for N and P and X. All right. You hit it and it just puts an open parenthesis. It wants you to put the three values separated with a comma. But you have to do it correctly. It's alphabetical. The N comes first, the P comes second, and the X comes last. If you put the numbers in the wrong order, well, you're going to get a wrong answer. NPX. Like I say, it's easy to remember. N comes before P in the alphabet, and P comes before X. And even P, if you think about it as being an R value, P still comes before R. It's alphabetical. In many cases, we will be interested in the probability of a range of successes. In such cases, we need to use the addition rule for mutually exclusive. For instance, let's say N is 6 and P is 0.5, and we're interested in 4 or fewer, right? Which would mean that I'd have to calculate the probability of exactly 4, add that to the probability of 3 successes plus 2 plus 1. You're saying, why am I adding? Well, it's this happening or that happening or the 2 or the 1. Now, we know that from the previous chapter when we're doing OR problems, the probability of this happening or something else happening, it's addition, the addition rule. So it would be quite a chore to use the binomial distribution formula to compute all the required probabilities. Table 3 and in the index, we could go through that, but that's going to be time consuming too. All right. There's no need of going to a table and figuring out all those answers and then adding them all together. All right. Here's a snapshot of it. I wouldn't want you to go to the back of the book and use all this. Likewise, you can find other values of probability of R from the table. In fact, for N equals 6 and P equals 0.50. These are the appropriate, either using the formula or going to the back of the textbook. There's a probability of all 4 right, 3 right, 2 right, and 1 right, or none right. Now, adding those up, it's tedious. It takes a long time. All right. What we could do, all right, here again, using pencil and paper, the probability of less than or equal to 4. Since there's 6 total events, what I could do is find a probability of 5. This actually should be an add sign. This should be an add sign, and this actually should be in parentheses. But I'm making uses of the complement rule. There should be a plus sign here, right? I could find a probability of 5, add it with a probability of 6, subtract that from 1, and that would give me the probability of 0, 1, 2, 3, or 4. All right. That's a mistake on my part. This should be in parentheses here, and that should be a plus sign, adding those two together and then subtracting from 1. We're going to do the same thing with the calculator. We're going to make use of the complement rule. And this will show you how that is accomplished. Here again, I'm not sure that this plays out of a video within a video. I'm not sure the sound would be recorded. So make sure that you're actually downloading the PowerPoint. Notice what I say, there's a slight error because the answer they're giving you is done pencil and paper, and there may be some discrepancy, but there's some discrepancy. It'll only be like by 1/10,000th. And I'll make sure on an exam that there are no two answers that are 1/1000th away. I'm not trying to be a clown about this. All right. The answers will be markedly different. I'm not going to put two that's going to be 1/10th or 1/1000th away. Make sure you watch this video within the PowerPoint. What's the probability of at least 4 seeds will germinate? The probability of a success germinating is 0.7. In this case, we're interested in the probability of 4 or more. All right, at least 4 means 4 or more. This means we have to compute P probability of R is greater than or equal to 4. 4 or more means 4, 5, or 6. Right? So I could individually find all three answers whether I'm using whether I'm using the formula or the table in the back. But we're going to see that just takes time. If I was doing the form, I have to do it 3 different times, and then add those answers together. All right. We already know the probability of 4, and using the calculator or the table, we came up with the probability of exactly 5 successes being 0.303, and a probability of 6 being 0.118. Now he simply adds all three of those together, probably of 4 or more. And adding them all up, we get 0.75. Now what's going to happen here, I'm going to watch the PowerPoint. I'm going to do that same problem, right, and get that answer without going to a back of the book for a table or using any formula. I'm just not sure that even if this did play out of this video, I wouldn't want to take the time to do it, make this video any longer than it has to be. Download the PowerPoint and it will do it all for you. All right, you're looking for 4 or more, 4, 5, or 6. So what I'm going to do in this video is I'm going to find a probability of either 1, 0, 1, 2, and 3. See, the probability of this happening plus the probability of that happening equals 1. So if I can let my calculator do this, subtract it from 1, then I'll have what I'm looking for. The calculator will not. It does something called cumulative, which means it starts at 0 and it stops where you tell it to stop. You can't tell the calculator, hey, to start at 4 and end at 6. All right, the binomial cumulative density always starts at 0 and ends where you tell it to end. The video is very informative about how this takes place. Make sure you watch it. We're still making use of the complement rule even in section 5.2. All right, there it is. All right, what I did here is to find the probability using the cumulative function, which is right below the p function, the probability function. I found this answer nicely from my calculator, and I took this answer, subtracted from 1. If I know this, I subtract it from 1, I get 4, 5, or 6. This is what I was looking for from Jump Street. I'm looking for the probability of 4. R is greater than or equal to 4. At least 4 means greater than or equal to 4. In a certain college, 33% of the students belong to an ethnic minority. If 10 students are randomly selected from the physics majors, what's the probability that no more than 6? No more than 6. So 0, 1, 2, 3, 4, 5, and 6 are good. 7's no good, 8's no good, and 9 and 10 are no good. No more than 6 means up to and including 6. Right, so there's 10 trials, probably of a success 0.33. Notice I'm using the cumulative. The cumulative will start finding probability of 0. It'll take that answer, add it to the probability of 1, with 2, with 3, with 4, with 5. And it'll go as far as 6. Add all those answers together. And notice there's a slight discrepancy. Boy, is this a lot easier than doing it with a formula going to a table. Right. Now, I granted this one here, there's an answer that's kind of close. I wouldn't have that on the exam. When you got 0.981, it'd be pretty obvious that 0.982 is your selection. I wouldn't even have anything this close. I'm not trying to play games here. Make sure you watch this because I walk you through it. I explain the whole thing, and I walk you through it in the PowerPoint. Just don't want to do it now because I'm not sure. Again, I want to be redundant, but I'm not sure if it actually plays. I'll find out as we move forward. All right, probability of at least 2 girls. At least 2 means 2 or more. So some of this actually requires that you take the English phrase and translate it to a mathematical phrase. And at the very end, I've got a slide that takes phrases and translates them into an inequality. I'll say it that way. All right, at least 2 means 2, 3, 4, 5, 6, or 7. I don't want to find each one of these individually, whether I use a calculator or I use a table and then add them all up. All right, and I don't even want even my calculator. I don't want to find 2, 3, 4, find these 6 and add them all up. What I want to do is to find the probability here. If I know this probability plus this probability equals 1. So my calculator can find that very easily. Take that answer, subtract it from 1, and I end up with getting what I need to get, probability of 2, 3, 4, 5, 6, or 7. All right. Probability, you got 7 trials, probability of success, boy or girl is 0.5. What you're not seeing there is the last number would be 1 here in this cumulative, and then I'm subtracting that whole answer from 1. This here again, I'll walk you through it. I actually show you. I'm being redundant, but you get the idea. These videos kind of important. There's enough of them here. Car insurance company has determined that 8% of all drivers were 8% of all drivers were involved in a car accident. Among 14 drivers in one particular street, we were involved in a car accident. If 14 drivers are randomly selected, what's the probability of getting 3 or more? Well, I don't want to find a probability of 3. Add it to the probability of 4, 5. All that takes forever. All right, so if I find a probability of either 0, 1, or 2, subtract that from 1, I end up getting the probability of 3, 4, 5. I'm going to use my calculator to find this answer right here by using the cumulative. It'll start at 0, it'll stop at 2, it'll add all these 3 answers. Taking that, subtracting it from 1, gives me what I was looking for from Jump Street. It's going to be a little creative here, using that the complement rule. Here again, this video walks you through it and does a nice job. And here's another one. This is the one I opened up with, that Wheel of Fortune. And what's the probability that the game show will have to pay it out to exactly 3 contestants? Here again, the video. You know the answer is 0.23. This is the video that shows you how that is done. Here it is. And is 100. Probably of a success landing in the gold is 1 chance in 36. You're looking for 3 successes. That's your ROI, as your calculator calls it the next value. Just recall, if you've got an 83, it's not going to prompt you like the 84 does. You have to remember, you got to put the n value, comma, the p value, probably of a success, comma, and then your r or your x value. It will not prompt you like the 84 does. So that video at the very beginning of this homework assignment walks you through all that. This is the sheet I was telling you. I would definitely have this by my side when it comes time for the exam, which will be a ways down the road. But it takes the expression and it changes it to an inequality, so you know what you're looking for. All right. 4 or more, at least 4, no fewer, not less than. All right. 4 or fewer at most, more than 4. That makes sense. So this is pretty handy. I don't say it's a cheat sheet, but it's a pretty handy resource. All right, that's the end of that. Be sure to download the PowerPoint.